Now let's quickly note that since delta R is just a multiple of I, when we dot delta R with our F average here, only the X component, only the I component of our function F affects the result. And the same is true on path 3. We're moving from here to here. We're dotting our F value with negative 0.03 I. So only the I component here contributes to this result. And that's in both cases because I dot j is 0. Similarly, on paths 2 and 4, the delta R vector is a multiple of the j vector. So when we dot with the average value of F, only the j component of F contributes to these results. Okay, so what is it that makes these different between path 1 and 3? It's the difference in the I components. Between path 2 and 4, the thing that makes these different, and by different I mean not equal and opposite, is the change in the j component. Because if this component didn't change between here and here, then multiplying by, or taking the dot product with 0.03i here and negative 0.03i here would give us no change. Okay, and the same with the j components here. If this didn't change, then since this is opposite, equal and opposite this, these two would be equal and opposite, and they would add up to 0, and we'd have 0 change over the whole path, over the whole closed path. Okay, now what is it then that makes the I component change between path 1 and path 3? As we've said, it's not the value of x. The value of x is the same here as it is here. It's the value of y. Okay, so what's going to cause this change, and what the change is actually going to be, is it's going to be the derivative of this I component function with respect to y. That gives you the rate at which the x, or the values of the function change as for a given x as you go from this path to this path. Now you want to think about that, you want to let that sink in, you want to think about that in many different ways, but that's what's going on. Okay, well, we introduce a little bit of notation here. Of course you've probably already seen it, but we let p be the multiple of I. So p is your x squared y function, and q will be the multiple of j, the x squared y squared function. And we're talking now about pi minus qj. The difference between the integral on this path and the integral on this path is due to p sub y, to the rate at which the function, this coefficient of I, the I component of this function, changes as y changes, because between here and here x isn't changing, y is. It's the rate of change with respect to y multiplied by the 0.05, which is the change in y. Okay, so py is the rate of change of this function with respect to y, and y changes by 0.05. Okay, well, we can calculate py. It's just x squared. That's very straightforward. So if we multiply x squared on this interval by the delta y of 0.05, we should figure out how much the function changes from here to here. And we see that, well, the py values, and we want to use an average value of py. When x is 1, py is 1. When x is when x is 1.03, p sub y takes a value 1.03 squared, 1.061. So on this interval and on this interval, the average value of py is going to be pretty close to 1.03. Again, doesn't depend on y in this case. So average value is approximately 1.03. We multiply that average value py by delta y, we get 0.0515. Okay? If we then take that change in the value of the p function due to the change in y and multiply that by the change in x, then we'll see what the net effect of that change is. So we multiply this, which is just an estimate of the difference between the values of our function on this interval versus this interval due to the change in y. If we multiply the difference in the function values, the average function value here and the average function value here, by the 0.03, we should get the difference between the path 1 integral and the path 3 integral, or the path 1 approximation and the path 3 approximation. And if we multiply those out, that's exactly what we expect. We get 0.001545. Now the difference between the path 1 and the path 3 integral, or the sum of the path 1 integral in this direction, the path 3 integral, which is in this direction, is negative 0.0015. So we're multiplying the change in the p values by the delta x to get the change, to get the difference between the integral in this path and the integral on this path. Okay, we do the same thing in the y direction, and we're going to get qx delta x delta y. Now the change here is going to be negative because we're subtracting this one from this one. We got into a lot of discussion about the signs of this thing. I'm just going to assert this now, and then I'll come back and talk about that. I don't want to digress too much. I'm just going to say that, okay, this product here should be the sum of the integral over path 1 and the integral over path 3. And that's equal to the negative of the integral of py with respect to area, because, and of course there's the astounding thing, okay, well, I should have made a bigger deal of that. This delta y delta x is just dA. So we have the result that the path 1 plus path 3 integral is just the integral of negative py over the area. And similarly, we can reason out that qx delta x delta y is equal to the sum of the integrals over path 2 and path 4, and that's simply equal to qx with respect to a over the entire area. Okay, I'm going to stop there, and then we'll come back and talk about a couple of the finer points and a couple of the details that I don't think I explained particularly well. We've got a general idea, but a little more detail on why the net integral over path 1 and path 3 is just due to this difference in delta y, and why we multiply that by delta x, and why I used a negative sign here, and I'm questioning whether I even should have done that. I kind of think I shouldn't have. So we'll come back and try to clarify that. And actually, in my case, it'll be tomorrow because it's pretty much the end of the day here and I'm getting a little fuzzy. Okay, so we'll come back and clarify all these details and see how they hang together.